Hi, this video is to demonstrate the design project submission for ECE 3201. I'm Kevin Knowles, and my partners for this project are Matt Silverman, Spencer Macri, and Paul Zemberski. The specifications we attempted to meet are an input impedance greater than 200 kiloohms, output impedance less than 100 ohms, differential mode gain with no loaded output of 65 or greater, common mode rejection ratio, no load, of 40 or greater, and a lower cutoff frequency, again with no load, of less than 300 Hz. So we'll start with maximum unloaded voltage gain. And the way this is set up is a pseudo-differential signal is being fed to the differential input, which is to say that one side of the differential pair is grounded, and the other side is being fed a common mode signal. The input and output signals are measured by the oscilloscope, and the results are as follows. Yellow traces the input, which is 10.4 millivolts peak to peak. Output is 700 millivolts peak to peak, which gives a gain of 67. And this amplifier has a highest gain at 2 kilohertz, so that's what I'm showing here. Now I've adjusted the function generator to put out 200 Hz instead of 2 kilohertz. This is to demonstrate the lower cutoff frequency, or rather that we meet the lower cutoff frequency requirement. So we're putting out 496 millivolts, and into the amplifier is 10 millivolts, and that gets us a gain of about 50, which is more than half of the maximum gain. Therefore, we have certainly met the lower cutoff frequency requirement. So now to demonstrate common mode gain and common mode rejection ratio. The amplifier setup has been adjusted so that both sides of the differential amplifier are fed the same signal, in other words, a common mode input. This is again at 2 kilohertz, and the common mode gain is now 1.4. That means the common mode rejection ratio is differential gain divided by common mode gain. 67 over 1.4 gets CMRR of 48. 20 log 10 of that to get decibels is 34 dB. So now the amplifier is set up to measure the input impedance of the differential stage in this pseudo-differential mode. The output of the differential stage is floating, it's not connected to the next stage, and the input of this differential stage is being fed through a 1 mega ohm resistor. So it's signal generator, 1 mega ohm resistor, then the amplifier. The yellow trace is the voltage coming out of the generator. The blue is the voltage between the 1 meg and the differential stage. Generator voltage is 22.8, the input to the amplifier is 4.4 millivolts, and that resistor that I've placed is 1 mega ohm. So current into this amplifier is 22.8 millivolts minus 4.4 millivolts divided by 1 mega ohm, 18.4 microamps. Therefore the input impedance is the 4.4 millivolts in divided by 18.4 microamps in, gets 239 kiloohms. The specification was 200K, therefore we have met the specification. So now we're set up to measure output impedance. The way this is set up is that the input to the final stage is grounded, and the output is being fed a signal in order to perform the measurement. The generator is hooked to the output through a 1K resistor. The yellow trace is the voltage on the generator side of the 1K, and the blue trace is the voltage on the amplifier side of the 1K. Voltage from the generator is 90.4 millivolts. Voltage into the final output is 11.6 millivolts, and that generator resistor is 1K. So from there we can calculate the current into the output. 90.4 millivolts minus 11.6 millivolts divided by 1000 ohms is 8.24 microamps. Therefore the input impedance is 11.6 millivolts divided by 8.24 microamps is 141 ohms. Specification was 100 ohms. So if I swap the 1 microfarad output capacitor for 10 microfarad and then adjust the signal generator so that we have enough amplitude to actually make a valid measurement, now we get a generator voltage of 216 millivolts. The input into the final stage's output is 4 millivolts, same 1K resistor on the generator. We get an input current of 216 millivolts minus 4 millivolts, all divided by 1000 ohms, gets 216 microamps. And then the input resistance is 4 millivolts divided by 212 microamps is 19 ohms, which far exceeds the 100 ohm specification. I believe that's everything, so I'll end the video here.